Hello, this is lesson 8 of Physics 30, charged particles in electric fields.
Thank you for the volunteer introduction. So, Physics 30, last lesson in electric fields. Here I want to point out that if we have a charged particle, the electric field strength is kq over r squared. That means, if you think about it, the field strength constantly changes because as the charged particle moves closer or farther away, the radius changes. So that means, okay, that the arrows get screwed up. Let me stop that. Now, anyway, sorry, what's happening here is the radius is constantly changing, or the distance between the charged particles, so the electric field strength, hence the force, hence the acceleration, will constantly change. Now, to solve this properly, it's a calculus question. Save that for Math 30-1. For the moment, what would you see on the Physics 30 diploma? It would be something like this. You place a proton 30 centimeters from a fixed alpha particle. What's the acceleration of the proton? So, reading the question carefully, proton, 30 centimeters, alpha particle, we're asking acceleration. So, for something like this, electric field strength, we can figure out quickly. Okay, good. Sorry, I thought there was, sorry, there's no extras? That sucks. Students, all right. Office go. All right, for the rest of you guys, here we have a proton, 30 centimeters from an alpha particle, or alpha plus 2, 30 centimeters, 0.30 meters. And this is a proton. Now, what's the acceleration? So here we have to figure out the electric field strength E and the force. Now, honestly, I'm getting lazy, so force is K Q1 Q2 over R squared. My apologies, we don't even have to figure out the electric field because that's MA. Now, do you know the universal gravitational constant? Oh God, it's not the gravitational constant, it is electrostatic constant, K. Do we know it? Do we know the two charges in coulombs? Yes. Do we know the distance between them? Yes. Notice we're talking proton. Do we know the mass of the proton? Well, you don't offhand, but go to your formula sheet. And we've got alpha particle, proton, 1.67 times 10 to the minus 27 kilograms. So, my question is, can you solve for the acceleration, or the instantaneous acceleration? Now, an equally important question, do we have to spend class time on that? Or can you do that calculation on your own? No, mass of the proton, and the chart, because we're talking about the proton moving. Okay, so, seriously, do we have to spend a few minutes solving this equation, or are you guys happy with this? All right, good. Now, most of the time on the diploma, what they talk about is uniform electric field between the parallel plates. And recall here the electric field strength, E, with the arrow, not energy, electric field, is force electric divided by charge, or voltage divided by distance. So, and remember the field strength is the same everywhere between the plates. So what we're doing here is we're ignoring this on the outside where it bends. Inside, it's all nice and parallel and the same. Okay? Excuse me. So far, so good? All right. Now, typical diploma question looks like this. Two parallel plates are connected to a battery. A sphere, 3.0 times 10 to the minus 15 kilograms, 2.6 times 10 to the minus 12 of a coulomb, is placed on the positive plate and released. Now, ignore gravity. Right. Now, what's the motion of the sphere? Well, the first things first, which one's the positive plate? Now, I went and double-checked. The little side of the battery is negative, and the big side is positive, which makes this the positive plate, and this the negative plate. I believe in my last video I screwed that up, or I said I couldn't. No, I said I couldn't remember, and I probably guessed wrong. So, welcome to my world. Okay, so we take our sphere and put it on the positive plate. what's it going to do? We repel because the direction of the electric field is that way. And a positive charged object will go that direction in the electric field. The negative charge will do the go in the opposite direction. So the motion of the sphere is. Now, can we say anything else about its motion? It repels and, oh, it's repelled by the positive plate, attracted to the negative plate. If it's repelled by the positive plate and attracted to the negative plate, what can we say about its motion? Negative direction. All right. Okay, plan B. What's its acceleration? Well, it's going to have there's going to be acceleration in there. V initial is 0. So V initial is 0. V final, we don't know. Okay. Now to calculate the velocity and that acceleration stuff, we look at the next question. What's the electric field strength between the plates if they're 4.5 centimeters apart? Now notice this is part B, so we're referring to part A, where I gave you the diagram. This is 2,000 volts. The displacement between them is 0.045 meters. So what's the electric field strength? Or I should say, what's the formula for the electric field strength? All right. There's 2 kq1 over r squared, or v over d. Now, here the problem is, oh, sorry, there's 3 of them. Force electric divided by the charge, or v over d. Now, the problem here is, this is for a point charge. First example we did back here, a point charge is like this alpha particle. It's a charge that we consider a point in space, and it's repelling or attracting everything. So as you get farther away from it, the field changes, gets less. So we don't have a point charge, we have 2 parallel plates. So what formula should we use? V and D, what do we get? Come on. You, the youngins with the calculators, tell me. No. On your calculator, you're getting 4.4444 e to the 44,444 volts per meter. Now, how many significant digits do we have? Here we argue 2,000. I didn't write it in scientific notation, so we can't say for certain how many. We can all agree there's the 2 in the 2,000 is significant. The first 0, I don't know, because I screwed it up. I really should have put it in scientific notation. And that's why you see the questions on the diploma, they always put it in scientific notation. Now, fortunately for us, for the moment, we don't have to round that off because that's the that answer we're using is input in another question. So no rounding off yet. Now, question C. Assuming the particle starts from rest, what is the particle's final velocity when it hits the negative plate? So it's going. Oh, poop. V initial, V final, acceleration, displacement, time. One of those darn things. Now, what can we say about the initial velocity? V final, we don't know. Do we know the acceleration? No. We can find out in a few minutes. Do we know the displacement? 0.045 meters, I believe. Do we know the time? No. All right. Now, how can we figure out the acceleration? Well, from force. Force electric is what? What's the formula for force electric? We've given a couple. Yep. EQ or MA. Now there is the other one, K Q1 Q2 over R squared, but that's for point charge, not parallel plates. Now, do you know the electric field strength? Yes, like we just calculated or something. Do we know the charge on the object? Yes. Do we know the mass of the object? Do we know the acceleration? Can we figure it out? So, acceleration is EQ over M, 44,444 volts per meter. Now, I have to peek back. 2.6 times 10 to the minus 12 coulomb. And the mass is a kilogram. Okay. So, everybody grab a calculator and tell me what the acceleration is, please. I got 3.81 times 10 to the 7. Okay, well, hang on. What did you guys get? 3.85. Okay. Times 10 to the 7 meters per second squared. Everybody get 3.85? Okay. So we have V initial, acceleration, displacement. I'm asking for V final. So you go back to physics 20. And if you're in the classroom, I'm now pointing at the kinematics poster on the wall with the laser pointer that doesn't work. There we go. And we go, we do not have time. So the only one without time is the bottom one. Velocity final squared equals velocity initial squared plus 2AD. That works. I think that's the easiest. Yeah. Now, if you don't like that one, someone will point out displacement is V initial t plus 1/2 AT squared, because V initial is 0. It's not a quadratic. So, oh, wait a minute, that's time squared. What am I smoking? We have to solve for time there. I don't want to, oh, we could solve for time and then go back and solve V final. I don't want to do that. Too much work. So, easiest way to do it, velocity final, velocity initial 0, 2 times 3.85 times 10 to the 7 meters per second squared times 0.045 meters. So what are you getting for final velocity here? Times 10 to the? Yes. And that, honestly, is not particularly fast for charged particles. If you have an old-fashioned cathode ray TV, the big glass screen and the big thing in back, we will do calculations later. You realize the electrons will be hitting that screen something like 10 to the 4, 10 to the 5, 10 to the 6 meters per second. Yes, supersonic, which is why it's in a vacuum, which is why you don't break the glass to let air in. Bad things happen when you do that. Anyway, notice we didn't calculate the time. I started to do that and realized too much work. All right, you're all okay with this? And now you see why they like this on the diploma. There's nothing particularly nasty, but lots of steps, including lots of stuff from physics 20 you're supposed to remember. All right? Now, other question would be, what's change in energy? Yes. Now this is change in E sub k, sorry. So that's change in kinetic energy. So that would be technically 1/2 mv final squared minus 1/2 mv initial squared, but mv initial, the velocity initial is 0. So So what are we getting here? And what is the mass of the particle? It's 1.9 times 10 to the 3 meters per second squared, which gives us 5.2 times 10 to the minus 9 of a joule, I think. Yes, it is. Dividing by 2 is the same as multiplying by a half. Okay, so y'all are getting 5.2 times 10 to the minus 9? All right, now I want to point out there is an easier way to do this. We did all these calculations to get V final, but where else have we seen energy in a formula recently? Yes. Yes. Change in voltage is change in energy divided by Q, the charge. So, because if you don't have to, if I just asked, what's change in energy? Here's change in energy right here. You don't have to do the acceleration and V final calculations. So you can do change in energy is change in voltage times charge. Now that was 2,000 volts, I believe, times the charge is, what was it? And I believe you get the same 5.2 times 10 to the minus 9 of a joule. Should get. All right. Now, if I just said what's the change in energy, that's the easier way to do it. If I was talking about what's the acceleration or what's the velocity, V final, it might be easier to do it the other way. But you can figure out V final from this, because that's 1/2 mv squared. In this instance, there's more than one way to do it. And depending on the question, I don't know which way to do it. You'd have to look at it. All right, so far so good? Okay. Now, here's a typical question you see on the diploma. So, a 5.0 times 10 to the minus 4 kilogram particle with a charge of plus 3 microcoulombs, my bad, is traveling at a speed of 350 meters a second, enters a uniform electric field as shown. If the plates are 5.5 centimeters apart and the potential difference between them is 1,000 volts, how far does the particle travel across? That is dx. So, here we have the particle traveling. It goes into the uniform electric field. What happens? The uniform electric field applies a force on the charge moves, goes down. Now, where have you seen an object traveling across and then going down like this before? Projectile motion in Physics 20. Yes, that's why they love this question on the diploma. And you just wait, because they're putting them in now where it's to scale and you have to measure it. They won't give you the data. You have to get a ruler and measure it. Yes, welcome to my world. Yes, and if you actually look at the homework questions I give you, you realize this was an 8-point question on the old diploma exam. It was written response. You'd have to do step by step by step, and now they're turning it into a 1-point numeric response. Woohoo! In case you're not getting that at home, there's sarcasm there. All right, but if you watch any of the videos, you understand that. Now, hang on. Shh. This question isn't bad because it's just projectile motion again. Now, those of you who did Physics 20 with me are looking at this and going, oh, God, not again. We did 100 of those back in Physics 20. Yes. Now you're doing 101. Those of you that didn't do Physics 20 with me, well, hopefully you remember this stuff. Now, Vx, dx, dx. V initial, Vy initial, V final y, acceleration of the y, displacement of the y, time in the y. Now, I'm cramming it in here so that we can look at the picture and the data at the same time. You guys at home, fill up the paper, please. Actually, I can cheat. Yes, I can. Ah, the advantage of having the pen. Everything over like that. There we go. Now, so what do we know? We know we know several things. We know, well, let's look at the data here. As I said, read the question. We have mass. That'll come in handy. We have charge, 3 microcoulombs. We have velocity initial. What is that? 350 meters a second, that is? No, that's what? Velocity in the x. Now, enters a uniform electric field as shown. Now, if the plates are 5.5 centimeters apart, what does this 5.5 centimeters tell us? Displacement in the y. Now, technically that's minus 0.055 meters. Negative down. Do I really care? No. You can call it negative going down, or you can call it going down. But a direction's helpful. And I gave you a voltage. We're asking for dx. Now, is there anything else we know that we can put into the table? Careful. No. Don't know the acceleration yet. What do you know? Yes. The initial velocity in the y direction is 0. It only starts to move once it goes into the electric field. Now, so here we're going E equals F over Q, which is V over D. Now, that's the formula you're probably going to end up using because force, now I really should be going force electric and talking about how this is vectors and all that. I'm just too lazy. So, and that's V as in voltage, not V as in velocity. This is normally where I make a joke about this would be a little easier if we were doing this in Cambodian with 126 letters of the alphabet. We wouldn't be repeating. Unfortunately, I have to learn to spell with 126 letters, which is, no, as my students know, no comment. Anyway, getting back to this, force, charge, voltage, displacement. We know the voltage. We know the displacement between the plates. I told you the charge, so we can figure out the force electric. And the force electric is ma. So we can figure out the acceleration because we also have the mass. Now, I have to go on to the next page to do this, and hopefully you've copied out the question. So, I was going to say here, F equals ma, and where was, oh yes, E equals F over Q, which is V over D. So force is VQ over D. All right. So force equals mass times acceleration, which is voltage times charge divided by the distance between the plates. That's just EQ, voltage divided by distance. Now, I'm feeling like rearranging the equation, then plugging the numbers in. So I'm going to go acceleration is voltage times charge divided by mass times displacement. Now, I feel like doing it this way, and since I have the marker, I'm going to do it that way. Yes, you can plug the numbers in and rearrange on your own, I don't mind. So plugging numbers in, what do we got here? The voltage is 1,000 volts. The charge on the object was 3 times 10 to the minus 6 of a coulomb. The mass of the particle was 10 to the minus 4 per kilogram. 10 to the minus 4. And the distance between the plates is 0.055 meters. So what are we getting for the acceleration here? One oh nine point. Okay. Round off 109.1 meters per second squared. That is, what, 11 times the acceleration due to gravity? That would take your average person and turn them into a smear on the wall. But this is a particle. It should survive it. And I'll give you gentlemen and ladies a moment to catch up. Do you all agree it's 109.1? All right, so yes. So we have to figure out time in the x in order to get displacement, which means we need time in the y. So going back, we have v initial, we have acceleration, we have displacement, we have time. We do not have v final. So the equation without v final in it is, yes, displacement is v initial t plus 1/2 at squared, I think. And I like this because v initial in the y is 0. So displacement is 1/2 at squared. Now, should I rearrange this and plug the numbers in, or just plug the numbers in? Okay. Now, actually, we've made a minor boo-boo. If displacement is negative, then the acceleration is also negative, the same direction. You figure that out. Now, I'm running out of space, so I'm going to continue this on the next page. So, what are we getting for time squared? And what are we getting for time? Come on, guys. Yes. So we end up with a negative displacement divided by negative acceleration minus 50, what is it? 54 point what? Whatever that is, and what do we get for time? Three what? Okay. I did ask for time squared and then time. 0.032 seconds. So 3/100ths of a second, that goes 5.5 centimeters, which, yes, explains the acceleration of 11 times acceleration due to gravity, or 11 Gs. So let's go. 350 meters a second in 0.032 seconds. 0.032 seconds. Velocity is displacement over time, or displacement is velocity times time. That's v as in velocity, not displacement, or not voltage, sorry. So that works out to be 350 meters a second. So what am I getting? Oh, wait a minute. I'm solving for time. Guys, help me out here. I'm supposed to be solving for... Never mind, you're right. Forgive me. Oh, getting old. What are we getting? Okay. So it goes 11.1 meters before it hits the bottom plate. Now, once again, I want to point out there's nothing particularly nasty about this, just horrible, horrible amount of calculations. All right. Feel okay-ish about that? Good, because I want to show you how they do it on the diploma now. So, yes. So, Okay, so, yes? You're moving 0.0, sorry, a student just asked, why do we not have consider the acceleration due to gravity in this question? And if you think about it, 0.032 seconds, how big is the acceleration due to gravity? Or how much would the velocity change due to that, due to gravity? No, this is something else. Sorry, where was I? Sorry, distracted there. Sorry, if you do the math, you realize the force of gravity is, well, it's 1/12 of the acceleration due to the plates. It's small enough we can ignore it. For 0.032 seconds, we don't care. Now, those of you at home are not seeing the grimaces on the faces of my students as I hand out this horrible diploma question. So as I said, this used to be a 8 or 10 point question on the diploma written response where you'd have to do a whole bunch of work and you'd point for this and a point for that. They've reduced it to 2 numeric response questions just to screw with you. I mean, no comment. So this is absolutely the nastiest it can get. So use the following information to answer the next few questions. And you notice they're putting everything in the bullet, in the box here, and the questions are down below. So 2 horizontal plates are separated by a distance of 5 centimeters. A beam of electrons is directed horizontally into the region between the plates. The path of the beam is deflected as shown below. Excuse me. Electrons in the beam have a speed of 9 times 10 to the 6 meters per second as they enter the region between the parallel plates. The electric field strength in the region between the plates is 3.0 times 10 to the 3 newtons per coulomb. And note this diagram is not drawn to scale. As I said, on the recent diplomas, they have been putting in some diagrams drawn to scale where you actually have to measure it. Yes. Well, sorry, a student just asked, what happens if you're a point off in your measurements? They would accept a range of values. Now, first question. The horizontal distance traveled by an electron in the beam in the region between the horizontal plates expressed in units of centimeters is blank centimeters. Now, I want you guys to work on this. How many centimeters does that beam travel? And then the second question, 2 physics principles must be used to determine the horizontal distance traveled by an electron in the beam. Using the numbers on the tarot data sheet, match the physics principles with the order in which they are used. There's more than one correct answer. Now, I'm going to pause the recording while you guys work on this. When you're done, come back and we'll check our answers, or compare our answers. Okay, ladies and gentlemen, here's the answer I got for this. Now, note a few things here. I set up a data table, X and Y directions. 5 centimeters, that's displacement in the Y, 0.020, sorry. My bad, sorry. Displacement in the Y, 0.02, because it's going up 2 centimeters. The 3 centimeters down is put in there to confuse you. Gentlemen? So, you know Vx is 9 times 10 to the 6 meters a second. Displacement in the Y is 0.02 meters, and Vy initial is 0. Now, since the electric field strength is 3.10 times 10 to the 3 newtons per coulomb, I figured out the electric force first. And I got 4.96 times 10 to the minus 16 of a newton. Then I found the acceleration. Acceleration is net force divided by mass. And I got an acceleration of 5.44 times 10 to the 14 meters per second squared. Now that gives me the initial acceleration displacement. I went and solved for time. So displacement is v initial t plus 1/2 at squared. It's not a quadratic because v initial is 0. And I got time 8.57 times 10 to the minus 9 of a second, which is reasonable if you're accelerating at 5.44 times 10 to the 14 meters per second squared. It's not going to take you very long to move 2 centimeters. Now, going back here, so that's time, 8.57 times 10 to the minus 9, and I got Vx. So I went down here and I figured out velocity, displacement, 0.07714. Now, a couple of students are arguing with me about getting 0.0772, and I'm fine with that as long as I can show the work. But the answer I got was 7.71 centimeters. Yes. Now, honestly, I don't know how much leeway they would give you on a question like this. They would have to. I wouldn't say have to, but I would assuming they would accept like 7.70, 7.72, where it's obvious you've done the work and done all the steps, perhaps a small rounding error. So there should be a small band in there or of answers they would accept. I don't know what it would be, but personally I would accept anything from 7.6 to 7.8 for this one. Okay? But be careful if you're rounding off. Now, the other reason I'm showing you this question, besides the fact I'm trying to scare you a little bit into doing your homework and handing it in, is the second question. Two physics principles must be used to determine the horizontal distance traveled by an electron in the beam in the regions between the horizontal plates. Using the numbers on the tarot data sheet, match the physics principles with the order in which they are used. There's more than one correct answer. Now, what they're talking about here, go to your data table, you go to, sorry, last page is formulas, second to last page, physics principles here. The data sheet, the constants, physics principles here. They always throw in one question about the physics principles. So, what principles do we use here? Well, we did uniform motion in the x direction and accelerated motion in the y direction. So the best answer for that is 1 and 2. Oh, sorry, 0 and 1, thank you. Or 0 and 1 or 1 and 0. 0 and 1, the other two. Never mind. So that would be the best answer, 0, 1 or 1, 0. Now, some people will stand there and argue with me about this because we could talk about conservation of energy and stuff like that, but no. That gets far too complicated. Really, the only thing I'm looking for is uniform motion and accelerated motion, 0 and 1. Okay? So that's the answer. That's how we get it. Please work on your homework. If you have any questions, see me in class. Thank you.